So that's a summary of the important formulae we obtained yesterday. On Wednesday, we had reduced hydrogen's problem to a one-dimensional Hamiltonian, 1 h sub L, 1 for every particular value of the total angular momentum quantum number L. And we found that this thing at the top here was a ladder operator in the sense that it, out of a state of a certain amount of energy and a certain amount of angular momentum, it constructed a state with the same energy and more angular momentum. And using that and the idea that this sequence of states of more angular momentum but the same energy had to stop, we concluded that the energy was given by a certain constant, 13.6 eV, divided by n squared, where n is one more than the maximum angular momentum that you can afford at that energy. Put another way, the angular momentum quantum number is less than or equal to 1 minus this number n that controls the energy and is called the principal quantum number. So what we want to do now is move forward to get the energy eigenfunctions, so to get the... These are of interest from the perspective of hydrogen. If you want to do any detailed calculations like how does hydrogen interact with the electromagnetic field, what happens if you scatter electrons off hydrogen, that kind of stuff, you'll need to know what these eigenfunctions, these wave functions are. But they're also the building blocks for studies of atomic structure generally. So they're a complete set of states which you can expand any state. For example, a stationary state of an oxygen atom, you can expand in these states. And that's what people do when they do atomic physics calculations, for the most part, what they do. So these play a very big role in atomic physics. Okay, so we want to find what they are. Now, from this, from the fact that L squared on E and L is equal to L plus 1 EL, from the fact that this state here of well-defined energy, the stationary state, is an eigenfunction of the total angular momentum operator, we know all about so the wave function in question is this, right? The amplitude defined at x, the atom when it's in this state, the reduced particle, strictly speaking, when it's in this state. We know all about the dependence, the angular dependence of this. We know that this takes the form of some function which presumably depends on the energy and on the angular momentum, times r times y L m of theta and phi. Because we know that the spherical harmonics, are the unique the eigenfunctions of this operator with this eigenvalue. So this thing, which we know is such an eigenfunction, its angular dependence must be given by, strictly speaking, a sum. Potentially it's a sum of these for different values of m and the same value of L, but it's sensible to look for them one by one, assuming a particular value of m and L. So the angular dependence, you know, out of that statement up there is this, and all we're looking for right now is the radial dependence. And the radial dependence, as I say, you have to expect it to depend on the energy. I mean, it has to depend on what's in here, which is the energy and the angular momentum quantum number. So that's what we're looking for, and we're going to get it just as we got the wave functions for the harmonic oscillator stationary states by studying the equation that this operator, your ladder operator, kills the thing off in the appropriate circumstances. So what we do is we look at the equation which says that AL, AL for the maximum value of L. So we're not allowed to make the maximum value of this is n minus 1. So if we use A, n minus 1 on E, n minus 1, we get nothing. It's the end of the line. So we look at this equation in the position representation, and so we can forget about that A0 over root 2 because it's just a constant. So what we want is we're going to be looking at I, PR over h bar minus, now I'm putting L equal to n minus 1, so that L plus 1, I suppose, is going to be an n over R plus Z over NA0, that operating on U n minus 1 must give you nothing. Now we know that PR is in the position representation. We figured it out. It was minus IH bar of d by dr plus 1 over R. So we put that fact into this equation. We have the I and the minus I make a 1. The H bars cancel. So we're looking at d by dr plus 1 over R minus this. So we're going to have minus n minus 1 over R plus Z over NA0 UN minus 1 is nothing. Now this is a prelims equation, right? It's a first order linear differential equation, so it has an integrating factor e to the integral of, with respect to R, of Z of this stuff, right? Just from prelims maths. This, of course, on integrating just gives me an R on top. This gives me a log R, and so we're looking at e to the minus some multiple of log R. So that means that this is going to become R to the minus n minus 1 from the e to the minus n minus 1 log R times the exponential that we get from there, e to the ZR over NA0. So now we know pretty much what's going on because the original differential equation, remember, says that d by dr of the integrating factor times u n minus 1 equals 0. In other words, this thing is equal to a constant. In other words, the wave function that we're seeking is a constant over the integrating factor. So we have that u n minus 1 is some constant, which must be determined by the normalization, times r to the n minus 1 e to the minus z r of n a0. So that's wonderfully simple expression. So let's ask ourselves a few things. Let's have a look at the ground state of hydrogen. So this is the case n equals 1. How do we know that? Because L has to be less than or equal to n minus 1. L is the numbers, the possible candidates for L are 0, 1, 2, blah, etc. So n has to start at 1 and then go up 2, 3, etc. So the ground state, the state with the least energy, is n equals 1. So what's the wave function? So u 1, and of course there should be a 0 here, is going to be a constant e to the minus. In hydrogen, z is 1, so this is just going to be r over a0. So the ground state wave function is this mere exponential, a beautifully simple result. What else was I going to say about this? Yeah. One interesting, okay, given that beautiful exponential, one thing you notice is that this thing is never 0. The ground state wave function has non-zero modulus all the way to r equals infinity, although the particle is classically forbidden to go beyond a certain radius. And in fact, so what this graph up here plots is the probability of finding the reduced particle at a radius r, measured in units of a0 over z there. So at a radius bigger than this, and the classically forbidden region stops at that number at 2. And it turns out there's a 24% probability that you'll find the reduced particle in the region that's classically forbidden, where the kinetic energy, as it were, would be negative, right? So if you go beyond r is 2, the potential energy is more than the total energy of the particle. So there's less than nothing left for kinetic energy, and there's a very significant probability of finding the particle that far out. So that's, I think, an entertaining result. It says that there's the P forbidden, is about 24%. Let's get the normalization of this thing sorted out so we can work out a few expectation values. Working out the normalization is fundamentally very straightforward. What we require, of course, we require that the integral d cubed x over all space of the complete wave function, which consists of u n minus 1 of radius, y lm, should equal 1. This thing we write, of course, as dr, r squared, and then the integral sine theta d phi d2 omega over the sphere. Oops, sorry, I should have mod squared this. Right, that's our requirement. When we integrate over angles over the sphere, we're integrating ylm mod squared over the sphere, and that comes to 1. So we're left staring at an equation which says that dr times r squared times u, this thing, squared. Now, what did we say that was? That was c squared. Well, we don't need to make it a modulus. We can declare it to be real. Times r to the 2n minus 1 e to the minus 2z r over n a0. So this should be 1. So the only thing to notice here is that there's an additional factor r squared. You don't just take the radial wave function, square it, and integrate dr to get 1. You have an additional factor r squared because fundamentally this is the normalization condition we wish to impose. And the ylms are normalized, so integrating over a sphere we get 1. So we've used here that the integral d2 omega ylm mod squared is 1. They're properly normalized. Now, this integral is nice and easy. So this can be written as c squared. And what we need to do is to bring an integral like this under control is to declare that this is rho. So we introduce a new variable rho, which is 2zr over n a0. And I want to make these, so what I have here is an r to the 2n, and I want to make all of those r's into rhos, which means I have to multiply by a load of factors n a0 over 2z. I've got r to the 2n from these two and another one from there, so it's 2n plus 1, and then I can turn all these into rhos, d rho to the 2n, where that's the definition. Oh, I'm missing the e to the minus rho. Now this is a famous integral in mathematics, which is, so it's often called gamma of 2n plus 1. I believe Euler's responsible for that absurdity, but what it should be thought of as is 2n factorial. So this integral, is simply this exponent up here factorial. Easy to prove. And you want to be able to recognize that because one often encounters that pattern, and you want to just be able to say, aha, that's 2n factorial. So this tells me what C is. C is equal to 2z over n a0 to the n plus a half, 1 over the square root of 2n factorial, which enables me to write down the relevant wave function u n minus 1 of radius. I need this factor here, and I'm going to write it as follows. I'm going to say this is 2z over n a0 to the 3/2 power. So I'm borrowing from that 3/2 power. 1 over the square root of 2n factorial. That's 2. I have to be clear. Sorry, I need a bracket there to make sure it's the whole 2n that gets factorialized. And then for the rest, these other factors, so the rest of the factors in here can be put together with those r's to make this rho to the n minus 1 e to the minus rho over 2. That's, see, rho is defined as 2z r, etc. So the factors left over from here are just what we need to make that, which was an r to the n minus 1 into a rho to the n minus 1. So what does this, physically what is this? We are looking at the states with the highest angular momentum for a given energy. So these are the quantum mechanical analogues of circular orbits, not eccentric orbits, but circular orbits. So what do we expect qualitatively? Well, we expect, classically, if it was a circular orbit, our probability would be a delta function at the radius of a circular orbit. And we know in quantum mechanics, everything's a bit blurry because steep gradients of the wave function are associated with large kinetic energies. So we're expecting it to be sort of like this-ish. So how does that arise from this formula? Well, when r is naught, rho is naught, this is going to be 0, and then it's going to shift itself off 0 slower and slower the bigger n is. So if n is 10 to the 30 or whatever it would be for a classical particle, then this would rise ever so slowly from 0, and it would hug the origin for a long time. It would then rise, and then when rho became on the order of 1, this exponential, which previously had been harmless, being e to the minus something small, would become a vicious cutting off thing, and that's how we get cut off on this side here. So here we're looking at rho to the n minus 1 growth, and here we're looking at e to the minus rho over 2, well, if this is the probability, then we need to multiply by, we need to square up, right? And this is an exponential decline. So precisely what it looks like is given in the next diagram. So the top picture there shows just the first 3. So the pure exponential is n equals 0, the ground state. Then the one that rises steeply at the origin and falls off after an early peak is n equals 2, and n equals 3 is the next one. And what you can see is that the characteristic radius is moving outwards quickly. So let's calculate some expectation values, because that's now easy to do. Let's work out the expectation value of the radius, right? So if we want to make a connection back to classical physics, we should be thinking about expectation values, because classical physics is the physics of expectation values. So this is easy to work out. It's going to be the integral dr r squared times r times u n minus 1 squared, right? That's what it should be. And now that we've got this normalization and everything sorted, we can evaluate this. So we're going to have well, actually, let's just go back to which is the best way to do this. All right, let's turn this all into rows. Let's turn these all into rows. Now, so this we've already got more or less as a function of rho. So what we need to do is to deal with these other ones. So there are 4 powers of r there, and I need to turn those into rows, which means I need an n a naught over 2z raised to the 4th power. Then I need to write down this thing mod squared, which is which is c squared, which is 2z over n a0 raised to the, so that's 2n plus 1, 1 over 2n factorial. That's the rest of c squared. Then we need the integral d rho rho cubed. That's these three, and then here we have rho n. I need to square that, so it's going to be n 2n minus 2 e to the minus rho. So what's this going to be? This is going to be 2n, this will be rho to the 2n plus 1 e to the minus rho. So this integral is going to be 2n plus 1 factorial. And on the bottom, I've got 2n factorial, so this on the top and that on the bottom gives me simply a 2n plus 1. Everything else cancels in the factorial. And here, something has gone wrong in that I've got far too many powers of n. What have I done wrong? What have I done wrong? Sorry, I got confused as to which one I was doing. Excuse me. I was using this formula here, which meant that the powers that I needed here, right, I was using this formula for u. These required these powers. Now I'm using this formula, so it's to the 3/2 power. To the 3, because I've squared it up, exactly. So we end up with, these three of these cancel, so at the end of the day, I'm going to have n a0 over 2z, just one of them, and we're going to have, what we said was this was 2n plus 1. In other words, we're going to have, if I put that 2 inside there, we're going to have n plus a half of a0 over z. So the expectation value of the radius is going sort of like n squared, and it's going like the scale radius we defined for hydrogen divided by z, which tells you that if you increase the nuclear charge, the size of the orbit's going to shrink like 1 over the nuclear charge. So the interesting fact here is that the expectation value of r is sort of like going like n squared, and that's exactly what we expect, because E, remember, goes like minus 1 over n squared. So therefore, it's going like minus 1 over expectation value of r. But we have a particle moving in a Coulomb field, so the potential energy goes like 1 over r. And from the virial theorem, we're expecting the potential energy to be minus twice the kinetic energy, so the total energy should be sort of a half, minus a half of the potential energy. So this is exactly what we're expecting. So that's a recovery of sort of classical-ish stuff. Interesting fact here is because this grows like this, it means the volume occupied by the atom is going like, which obviously goes like the expectation value of r cubed, which goes like n to the 6th power, is growing very rapidly with n. So states, so this grows very rapidly. This means that states in which you excite the electron to a large value of n cannot be seen. You won't be able to observe these, to measure these, unless you're in an incredibly high vacuum. So e.g., if n's 100, the volume is going to be 10 to the 12 times a regular atomic volume. And in interstellar space, you can see hydrogen atoms transitioning from n is 100 to n equals 99 and stuff like that by making measurements at radio wavelengths, centimeter wavelengths, but you can't do that kind of thing in a laboratory because you can't get a high enough vacuum. So in the laboratory on Earth, we're restricted to relatively small values of n. N less than 10, typically. Right. What else can we say? What about it's interesting to work out the expectation value of r squared. It's essentially identical performance to what we've just done. I mean, all we have is an extra r in that integral at the top there, right? So what are we going to have if we come down here? We will have an n a0 over 2z raised to the 5th power this time, because we're going to have an extra power of r before the u starts. Then we will have 2z over n a0 to the 3rd power coming from the u. Then we will have our 2n factorial coming from the c. And then we will have to do the integral d rho. And we'll have an extra power of rho. So it'll be rho to the 4th times that rho to the 2n minus 2. So we'll end up with rho to the 2n plus 2 e to the minus rho. In other words, this is going to be 2n plus 2 factorial. Right, so now we're taking 2n plus 2 factorial, not 2n plus 1 factorial, dividing by 2n factorial. So this is, and we're going to get an extra power here. So this is going to be n squared coming from here, because this 5th power will be reduced to the 2nd power by when we multiply this on. So we'll be left with n squared a0 over 2z squared. And then we will have 2n plus 2, 2n plus 1. It's interesting to express that as a multiple of the expectation value of r, which we've already derived, as being nn plus a half a0 over z. So a0 over z is essentially expectation value of r. So this is going to be, these 2's I can take out. There are 2 2's in here. I take them out and use them to clean that up. So this is going to be n squared, n plus 1, n plus a half of a0 over z squared, which itself is the expectation value of r squared over n squared, n plus a half squared. So we can cancel many things, and we find that that's n plus 1 over n plus a half of the expectation value of r squared. So what does that mean? That means that the uncertainty, well, so what's the RMS variation in R? Now you'd think this thing would go to 0, right? Because what we're doing is we're looking at the quantum mechanical analog of a circular orbit. Circular orbit, the particle does not move in and out. So we would expect that this RMS variation in R went to 0 as n went to large values, and we would have thought we would recover classical physics. We'll see that that's not the case. Because what is this RMS variation? Well, it's r squared expectation value minus r expectation squared. Take the square root of that, okay? So here is the expectation value. Let me write it in again. R squared expectation. So all I want to do is from this, I want to take r squared and then take the square root. So this is equal to the square root of n plus 1 over n plus a half minus 1 expectation value of r. So you can easily see that this is going to come to something like the square root of a half over n plus a half of the expectation value of r. So what's happening is that the RMS variation in the radius is becoming small with respect to the radius relative to the expectation value of the radius, but jolly slowly, right? That's on the order of expectation value of r divided by root n. So it's becoming small relative to the radius itself, but only slowly, but it's absolutely large, right? This, because this thing is growing like n squared, this is looking like n to the 3/2 power. And I think you can just about see that in those pictures up there, that as you, well, I've only shown the first 3, but you can't see the peak becoming narrow. It doesn't become narrow. So that's a remarkable result. Okay, so those are the wave functions for the essentially circular orbits. What about the non-circular orbits? As we see, they're not very circular, but that's the best we can do. So how do we expect to get these wave functions for non-circular orbits? Well, in the case of the simple harmonic oscillator, we found the ground state wave function by solving A on ground state wave function equals 0, and that's essentially what we've just done. And then we found the excited state wave functions by taking that wave function we first found and multiplying it by A dagger an appropriate number of times. And every time we multiplied by A dagger, we got a more complicated wave function, right? So the ground state wave function, the harmonic oscillator, was a Gaussian. The ground state wave function here was well, this is a slightly more complicated problem. This is a more complicated problem because we have all these different values of the angular momentum. So here, our starting point is r to the L is r to the n minus 1 times an exponential, as in the same sense that our starting point in the case of a harmonic oscillator was just a Gaussian. But that's the strategy. And what we would hope is that AL dagger does the business, right? AL increased our angular momentum at fixed energy and drove us up against the equation that we solved to find the circular orbit wave function. And AL dagger, we would hope, would move us from the circular wave function back down to more eccentric orbits. But this has to be done in a slightly subtle manner. Okay, so let's look at at a formula that we have here somewhere. Let's look at this formula here. AL, AL dagger is equal to the difference of h's. So let me write that down with L reduced by 1. AL minus 1, AL minus 1 dagger, this is just a relabeling operation, right, is equal to, can I remember which way up it is? No. A0 squared over mu, A0 squared, mu over h bar squared of HL minus HL minus 1. Now let me take the dagger, let me commute this entire equation, both sides of it, with respect to AL minus 1 dagger. You'll see why we're doing this when we've done it. So we're going to say that this is AL minus 1, AL minus 1 dagger, AL minus 1 dagger. So that's the left side of the equation commuted with AL minus 1 dagger. And that's going to be boring constant times HL, AL minus 1 dagger, which is what I want, minus HL minus 1, AL minus 1, minus 1 dagger. Why am I doing this? I'm doing this because I want to calculate this, which we haven't so far calculated. We could calculate by going back to first principles and stuff, but working out these commutators is quite wearisome. So it's best, this is a reasonably slick route. But what I want to do is calculate the commutator of this with h sub L, and what I know at the moment is only the commutator of this with HL minus 1. Okay. So I'm going to rearrange this equation now, because this is my target, as HL, AL minus 1 dagger. That's what I want to find the value of, because it'll turn out to be the key, is equal to h bar squared over A0 squared mu, open a big bracket. Then let's write this out, turning this into its product. So I'm going to expand this inner commutator. As a general rule, I hate to expand commutators, but you'll see in a moment that it's an expedient thing to do. So this is going to be expanded, and it's going to be AL minus 1 times AL minus 1 dagger. Still the outer commutator in place, so commuted with AL minus 1 dagger. Close that bracket. minus, is there room? Yes, minus the commutator a L minus 1 dagger, a L minus 1 comma a L minus 1 close brackets, dagger. Sorry, that one's dagger, right? It's this one here. So all I've done is taken the contents, I've taken this inner commutator and expanded it into its 2 bits. And then I should bring this onto this side of the equation, step 1. Step 2, replace this h with the corresponding expression in terms of a dagger A, right? So A dagger A, it says up there, is a multiple of HL plus a constant. I'm interested in HL inside a commutator, so I don't need to care about that constant because it will commute with everybody and produce a vanishing commutator. So for my purposes, I can merely replace HL by AL dagger AL times that constant. That constant is already present and correct. So this term here becomes minus AL, gosh, which way around is it? It's dagger on the left, yes. AL minus 1 dagger, AL minus 1. So that's this. Together with this, that's this. Inside a commutator, comma, now this. A dagger, L minus 1. Close commutator, close big bracket. Now we should find that 2 of these terms cancel. They don't. This is a minor catastrophe. Oh, because I brought it onto the other side of the equation. Thank you. Yep. The people are following. So I brought this across here. No, but I thought I allowed. Oh, she said it arrives with a plus sign. It arrives with a plus sign. Of course, it arrives with a plus sign. Brilliant. So we can kill. So these two fight each other and leave a blank piece of board. So what do we need to do now? What we need to do is concretely evaluate this commutator, right? Because so these two kill each other, and we're left looking at this. This is the usual commutator of a product rubbish. So what we have is, so I'll write it down explicitly because it is a bit of a mess. A0 squared mu, A L minus 1, comma, A L minus 1 dagger, commutator, right? He works on this one while he stands idly by. And the other term vanishes because everybody commutes with themselves. So we don't need the big bracket because that's the end of the discussion. And all we have to do now is plug in what this is, because it turned out to be the difference of the two, right? It's the difference of the two Hamiltonians. So this is h bar squared over a naught squared mu of h L minus h L minus 1. I have to do a little translation because this is L minus 1 times a L minus 1 dagger. Okay, so now with that expression, we can go to business because we can. Sorry, should have gone away? The constant out the front should have gone away, exactly. It was what I needed to, yes, there was that constant the other way up there. Thank you very much. We'll get rid of that. So we have an unbelievably simple result after slightly scary computation. So what do we do with that? What we do with that, of course, is we go and say that A of A L minus 1 dagger E L is equal to A L minus 1 dagger H L E L. Right, so H L E L is E E L. Multiply both sides of the equation by this baby, and we have what we've got on the board. Now, of course, we're going to swap these two over. So we write this as HL AL minus 1 dagger plus, so we're not allowed to write that down, so we put in what should sort it out, which is the commutator AL minus 1 dagger, comma, HL, close brackets, 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 EL. And this is what we've just laboriously worked out and found is HL minus HL minus 1, right? So this is going to give me an HL minus HL minus 1 times A, crucially, times HL minus 1 subscript times AL minus 1 dagger. That's that, right? So this expression goes in where that commutator is. We can see, the commutator is the other way around. Yes, the commutator up there is HA, not we want AH. So this becomes a minus, exactly. So the undesired terms, which are this on this, cancels with this on this, and we are left with minus minus is plus, HL minus 1, AL minus 1 dagger EL, which is the equation that we require because it says that this object is an eigenfunction of this operator with the same old eigenvalue, right? So this establishes that EL minus 1 is actually equal to is some multiple of, to be discussed, AL minus 1 dagger EL. And that enables us, by mere differentiation, by just using more and more of these, to work our way from the circular orbit wave function down to the wave function associated with no angular momentum at all. And let's just begin to see how that pans out. So let's ask ourselves about, so UN n minus 2, you should get by using this AL dagger stuff on U n minus 1, which we already know what it is. So that's proportional to, I'm not going to chase down these proportionality constants now. Ain't time. It's proportional to now we have to think what to put in here. This is the angular momentum with which you arrive. And I'm interested in arriving with n minus 2. So this is going to be n minus 2 dagger operating on the wave function associated with where we were before, which was n minus 1 of radius. Let's write that out in the position, well, it's more or less in the position representation, but let's be more concrete about it. So let's find our expression for AL. We're not interested in the constants in front because we're going to normalize this when we're all sorted. So I want the Hermitian adjoint of, I want the dagger of that thing at the top there. So this is equal to minus I PR on H bar minus, now what's L? We put L equal to n minus 2. No. Yes, this is L. It's been put equal to n minus 2, and I'm supposed to have L plus 1 there. So I'm supposed to have 1 more than this. So that's n minus 1 over R plus Z over, is it n minus 1? Yep, A0. Close a bracket. What's that working on? It's working on this, which is R to the n minus 1, e to the minus Z, e to the minus Z R over n A0. Hope I did that right. So now we have to gain to replace PR with minus IH bar d by dr plus 1 over R. So we're going to have too many minus signs now. We'll get a minus d by dr minus 1 over R coming from here, minus n minus 1 over R, plus Z over n minus 1 A0, close brackets, R to the n minus 1, e to the minus Z R over n A0. So we could write this taking out an overall minus sign to make life a bit less negative. This is n over r minus z over n minus 1 a0 r n minus 1. Okay. So what's going to happen? The important thing is to understand what's going to happen. This is a particular value. This is a specimen of the AL dagger sort of thing, right? If we change n, L, we'll be changing this number here. But the main idea is, what's crucial, is that this is going to contain, every one of these is going to contain a derivative operator. When the derivative operator meets this, it will produce a term which goes like r to the n minus 2. It will produce a term which has less r dependence. Also, there is this something over r term does the same thing. So we get an amount of r to the n minus 2, but we also get from this, or from differentiating the exponential, we get an amount of r to the n plus 1. N minus 1, sorry. So in other words, and of course the exponential will live on in the way that exponentials do when differentiated. So what does the wave function look like? U n n minus 2 is now a linear function of radius. It's going to be a plus b r. And actually that will be negative. Let me write it. I mean, concretely it's going to be negative. Times r to the n minus 2, so I've taken this out, e to the minus zr over n a0. So since this is a linear function of r, and moreover b and a are positive, we get one node, right? So that is to say, u of some particular radius vanishes. When we go to get u n minus 2n, sorry, minus 3n, we'll use another of these differential operators, and we will find that this is some, it'll be sort of a primed minus b primed r plus c primed r squared. It'll be a quadratic expression, e to the minus stuff, and we will have two nodes, because it'll turn out this quadratic has real roots, and so on and so forth, right? So every time we use an A dagger, we get one more node. Why is that physically? What we're doing is we're taking kinetic energy out of the tangential motion, remember, and stuffing it into the radial motion. And kinetic energy, motion in quantum mechanics is associated with oscillating wave functions, so we're getting more and more wavelengths radially, and therefore more and more nodes radially. And here is a picture of what a few of these things look like. So, oops, these are the wave functions, the radial wave functions. Well, this is a picture of the meridional plane. So this is radius here, and this is z direction here, okay? So we're discussing, the wave function in question is filling a volume, and it can, right. So that's kind of how you should think about it. This is the circular orbit case. Blackness means high probability of finding the electron or the reduced particle. Whiteness means not much. So this is the circular orbit. It's 0 on the axis because, you know, we saw it was 0 on the axis before. It's reasonable. It's got a lot of tangential motion. It can't get to the axis. But then otherwise, the amplitude of finding it rises quite quickly, peaks, and then very slowly falls away as you go off to infinity. But it's rather boring, right? It's sort of everywhere. If we, using an A dagger, an A n-2 dagger on this, we get this wave function. This is for the case n equals 3, by the way. We get this situation where we have one radius. This is the node. So it rises at the origin. It peaks sooner, so it reaches a high peak at a smaller radius than this, which is associated with the fact it's on a more plunging orbit, right? It has a pericenter. But then quantum mechanically, it has this node where you won't find it. You have 0 probability of finding it around that circle, and then you have a probability of finding it further out. Use another of these A dagger things, and you'll come over here where you have 2 nodes. Here you see them. And now, in this case, because n is 3, you've run out of energy. in this case, there's no orbital angular momentum, there's no tangential motion. This is what a plunging orbit looks like in quantum mechanics, right? That particle in classical physics will be just diving at the nucleus, slipping around it and coming back out again in an arbitrarily elongated ellipse. So it doesn't look at all like that. Well, that is clearly the moment to stop with that review of the hydrogen wave functions.